Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So in this class, we'll discuss about the antenna arrays. One of the major problem with the single antenna is that once you design the antenna, you fabricate and you cannot change the radiation pattern of the antenna. So once the antenna is fixed, antenna is designed, constructed, you cannot change the radiation pattern. Radiation pattern is fixed. So if you want to change the radiation pattern, then you can apply a technique called antenna array. Instead of having one element, you can have many element antenna, and you can fit the antenna with different phases, current. Then you will be able to even modify the radiation pattern of the antenna array. So basically, antenna array composed of multiple antennas, and depending on what kind of current you are feeding to every antenna in the antenna element in the array, you will have a different radiation pattern. So now this antenna array can be of different shapes. It can be linear in a line. You can arrange all the antenna element in a line or in a circle or in a plane. So depending on the shape, you can differentiate different kind of antennas: linear, circular, planar, etc. And you also will have different antenna array for different element spacing. Depending on the element spacing, your antenna array performance is going to change. So these are some of the antenna array design parameters. One is the array shape, what kind of shape you want for the antenna array, how much should be the distance between the antenna elements or element spacing, and what excitation you are giving to every element of the antenna, what phase, current excitation, current phase you are giving to every element of the antenna. So these are some of the parameters with which you can design the antenna array. So let's look at this structure. So this structure is the antenna element array. So basically we have three elements here, element 1, 2, 3. So now so in the element 1, what are the amplitude of the current and phase you are giving? That will decide the pattern of the antenna array. Then what are the other parameters? We also have the pattern of the array element. Depending on what arrangement you have for the array element, it could be circular, linear. So your antenna pattern is going to be different. And this spacing also plays a significant role, and the shape of the array. So in this case, you can have circular also, you can have different shapes. So basically here there is a very fundamental principle which is called pattern multiplication principle. What does this principle says? This principle says that you know the pattern of an array element. Let's say you are making an antenna array of identical array elements. In that case, you want to find the radiation pattern of the overall antenna array. All you need to do is find out the pattern of an individual array element and multiply by a factor called array factor. So you multiply individual antenna array element radiation pattern and you multiply by the array factor, you should be able to get the radiation pattern of the whole antenna array. And this array factor is dependent on the geometry of the geometrical arrangement of the elements in the array and what kind of excitation of current, amplitude and phase you are giving to every element. So let us first start with the simplest one. Let's start with the two element array. So that means in the antenna array we'll have only two elements, and you assume that the two elements are infinitesimally small current carrying element Hertz dipole which are positioned along the z axis, and you want to find the field somewhere in the far field of the antenna. So now this is the structure. Let's look at the structure first. This is one Hertz dipole and this is another Hertz dipole. This is the origin. Now you are placing this Hertz dipole at a distance d by 2 from the origin, and this Hertz dipole is placed at a distance d by 2 minus d by 2 from the origin. So this is minus d by 2, this is d by 2 along the z axis, and Hertz dipole are directed along the z axis. So now what we are trying to do is find out the field produced by this Hertz dipole and this Hertz dipole in the far field of the antenna. So P is a position vector. We are looking at the radiation of this Hertz dipole 1 and 2 at the far field position P. So how do I find out that? So that's very simple. You see, you know what is the radiation pattern of a Hertz dipole. So you find out the radiation field of a Hertz dipole. So you know what is the radiation field of a Hertz dipole. You find out the radiation field of this Hertz dipole at position P, and you also find out the radiation field of this Hertz dipole at position P. You sum them up, vectorially sum them up, you get the total radiation pattern of this antenna array, 2-element Hertz dipole. So let us do that. So total electric field in the far field will be electric field produced by the Hertz dipole 1 and electric field produced by the Hertz dipole 2. You sum them up. So you know that Hertz dipole gives linearly polarized wave along the theta direction. So both of them will be along the theta direction. This also theta direction. This is the expression for the radiation field of a Hertz dipole in the far field. R1 is the distance of this Hertz dipole 1 with the observation point. R2 is the distance of the Hertz dipole 2 with the observation point. R is the distance from the origin. So you have R1 here, so R1 here. Then current supplied for the Hertz dipole 1 and 2 are different. Let's say the current given to the Hertz dipole 1 is I1 exponential j delta 1, and the current which is supplied to the Hertz dipole 2 is I2 exponential j delta 2. So two antennas are excited with current I1 phase of delta 1 and I2 phase of delta 2. So if you assume that the current which is supplied I1 is equal to I2 is equal to I0, and even the phase delta 1 is alpha by 2 and delta 2 is minus alpha by 2, then you can simplify the expression of the total electric field by taking out the common terms. What you have is this term here in the first bracket. So you can look at this. This looks like exponential j theta plus exponential minus j theta kind of thing. So you apply the Euler's theorem. This will become twice cosine of beta d by 2 cos theta plus alpha by 2. So this is the expression for the electric field of the 2-element Hertz dipole in the far field. It will be directed along theta direction, and you have a term here. So now if you look at it, this expression looks like the radiation pattern of a Hertz dipole, and this expression we usually call this as an array factor. So now in this case what we have observed is for 2-element Hertz dipole the array factor is this. So from the pattern multiplication principle, what do? You want to find the total electric field of the antenna array. In this case is a 2-element Hertz dipole antenna array. What you need to do is just find out the electric field pattern of the single alone Hertz dipole multiplied by the array factor. Array factor for the 2-element antenna array composed of Hertz dipole is this. So this is the array factor. So now usually people consider array factor is normalized, so the maximum value it can have is 2. So you divide by 2. So array factor normalized with respect to 2 is this, cosine of half beta d cos theta plus alpha. So now that was the simplest case when we have 2-element antenna array composed of Hertz dipole. Let's say if you have a n-element antenna array arranged in a line. So those kind of antenna array we call it as n-element uniform linear array. Uniform because the distance between one Hertz dipole to another Hertz dipole is equal. Spacing between the antenna elements is fixed. That is d, denoted by d. D is the distance between the antenna elements. So let us try to find the array factor for a n-element uniform linear array, ULA. So in this case we have n Hertz dipoles which are placed along a straight line along the z-axis at position 0, d, 2d, n minus 2d, n minus 1d respectively. So this diagram will clarify that. We are considering uniform linear array. This is the first Hertz dipole, second, third, and so on. So distance between this and this is d. So we have a Hertz dipole at 0, Hertz dipole at d, 2d, and so on up to n minus 1d. And we also supply current I with 0 phase. Here we supply current I with alpha phase, then 2 alpha, and so on. So this is the uniform linear array we are considering. So now for this uniform linear array 1, we'll consider another case uniform linear array 2 later on. So let us try to find out what is the array factor for this. So you can simply find out array factor would be for the first antenna, the contribution in the array factor will be 1. For the second antenna, the contribution will be plus exponential j beta d cos theta plus alpha. D is the distance between the antenna element, alpha is the phase shift you are giving. For the third element, it will be exponential j 2j beta d cos theta plus alpha. And for the last one, it will be exponential jn minus 1 beta d cos theta plus alpha. So now this looks like a geometric progression. No? So for the geometric progression, you can find out array factor will be summation n going from 1 to capital N. N is the number of elements, exponential jn minus 1. This is a small n here. Small n is going from 1 to capital N. Beta d cos theta plus alpha. So this is a geometric progression. You can simply find out array factor for n element uniform linear array is 1 minus e exponential jn psi divided by 1 minus exponential j psi. Psi we can denote this as beta d cos theta plus alpha. That's a compact notation of beta d cos theta plus alpha. So the array factor turns out to be 1 minus exponential jn psi divided by 1 minus exponential j psi. So now this one you can take out common exponential jn minus 1 by 2 psi. In that case, the expression will become like this. See again, you can even express this one also. So when I take out exponential jn minus 1 by 2 psi, so in that case, see basically from the numerator you take out common exponential jn by 2 psi. From the denominator you take out common exponential j half psi. In that case, what common you are taking is exponential jn minus 1 by 2 psi. In that case, the numerator will become this, denominator will become this. So this looks like your sine function. So this will become sine of n by 2 psi. This will become sine of psi by 2. So now we have array factor as sine of n by 2 psi divided by sine of psi by 2. And we have another extra term here. So now if I want to get rid of this term, what I need to do is another arrangement of the uniform linear array in which I actually put half of the antenna element in the positive z axis and remaining in the negative z axis. Let's say n is an odd number, then I put half of the array element in this portion and the remaining half here. And at the origin also we have a Hertz dipole, so n minus 1. So n is the odd number, then n minus 1 by 2, n minus 1 by 2 in the upper positive z axis and n minus 1 by 2 in the negative z axis, and at the origin we have 1. So total will be n minus 1. Total would be n minus 1 by 2 in the negative z axis and n minus 1 by 2 in the positive z axis. Total would be n. We also have 1 at origin. So if we make that kind of arrangement, this extra term you have here will be gone. So in that case, array factor will simply become sine of n by 2 psi divided by sine of psi by 2. And again, you can make simplification for small values of psi. For small values of psi, sine function can be represented by simply its argument. Sine of theta is equal to theta when theta is a very small number. So sine of psi by 2 you can write as psi by 2. So again, you can normalize it. You can also normalize it. So if you normalize it, then you need to divide by 1 by n. See, in order to normalize it, you need to find the maximum value of the array factor. So array factor, when psi is equal to 0, it is indeterminate. So what you have is 0 here, 0 here, 0 by 0 form indeterminate. But you can use L'Hopital rule, and you can find out the maximum value. Maximum value turns out to be n. So array factor normalized will be 1 by n sine by n by 2 psi divided by sine of half psi. So now what you can see here is, for small argument psi, this will become n by 2 psi. So this is the array factor. What does this look like? This looks like your sinc function, no? So this normalized array factor for uniform linear array, what are the properties? Let us try to look at. As n increases, main lobe narrows. The main lobe will become narrower and narrower. So now we have a control over the radiation pattern of the antenna array. Unlike that of a single antenna element, you cannot change it once you have manufactured it. But if you have an antenna array, you can control the radiation pattern. If you increase the n, that means number of elements in the uniform linear array, if you keep on increasing it, the main lobe will become narrower and narrower. The number of lobes is equal to n. Total number of lobes is n. We'll have a one main lobe and other n minus 1 side lobes. Total number of lobes is n, one main lobe and n minus 2 side lobes. The width of the side lobes are 2 pi by n, and the main lobe will be 2 times wider than the side lobes. And if you keep on increasing the number of elements in the uniform linear array, the side lobe level will also decrease. So let us try to find the null of the array. Null of the array, that means in the radiation pattern of the antenna array, is there any null? Is there any angle at which there is no radiation at all? So for the null of the array factor should be equal to 0. If array factor is equal to 0, then sine of n by 2 psi is equal to 0. What was psi? Psi was beta d cos theta plus alpha. So now when psi becomes 0, n by 2 psi becomes 0. See, sine of n by 2 psi becomes 0 when n by 2 psi equal to plus minus n pi. Sine of n by 2 psi becomes 0 when n by 2 psi becomes plus minus n pi. And you know what is psi? Psi is beta d cos theta plus alpha. Plug it in here. Then what you have is beta d cos theta is simply minus alpha plus minus 2n pi by capital N. So if you want to find out the theta null, theta n is equal to cosine of inverse 1 by beta d minus alpha plus minus 2n pi by capital N. You can take values of n as 1, 2, 3, 4, 5 and so on. You can find out the null of the array pattern now. That would be cosine of inverse 1 by beta d minus alpha plus minus 2n pi by capital N. You can also find out the maximum value of the antenna array radiation pattern. What is the value of theta for which you have the maximum radiation pattern for the antenna array? So for the maximum, psi by 2 should be equal to 0. So in that case, half beta d cos theta plus alpha is equal to 0. Theta maximum is for cosine of inverse equal to minus alpha by beta d. Alpha was the phase shift, beta is the wave number for free space, d is the distance between the antenna element. So now you know where is the location of the maximum value and the null of the antenna array for the uniform linear array. So let's say if I want to have a broadside array, so I have the liberty of choosing what kind of pattern I want to make from the antenna array. Let's say I want to have a broadside array. Broadside array means I want to have maximum radiation at the theta is equal to pi by 2. So that means broadside array theta is equal to pi by 2. How can I do that? When I want to have a maximum radiation at theta is equal to pi by 2, in that case, see, psi is equal to 0, we have the maximum radiation pattern. So I want to have maximum radiation pattern at theta is equal to pi by 2. So theta becomes pi by 2. What should I do? If theta becomes pi by 2, then what should I do? Alpha should be equal to 0. If I want to have a broadside radiation pattern, the phase shift I am giving to each Hertz dipole should be equal to 0. There should not be any phase shift. All the Hertz dipoles should be supplied with the same phase. Then I will have a maximum radiation along the broadside direction. let's say I want to have an n-fair array. N-fair array means I want to have maximum radiation along theta is equal to 0. So in that case, you know that maximum radiation occur when psi is equal to 0. So beta d cos theta plus alpha is equal to 0. Theta is 0 now. In that case, what happens? In that case, what I need to do is alpha should be equal to minus beta d. So the phase shift I am giving to its antenna element is dependent on alpha. The first one I am giving alpha, second one I am giving 2 alpha, and so on. That alpha should be decided like this: alpha equal to minus beta d. So in that case, I will have n-fair array. Maximum radiation will be along the n-fair direction. We can even have phase scanning array. So I want to have a maximum radiation pattern of the antenna array at one particular angle theta 0. It could be any arbitrary value theta 0. It could be 0, pi by 2, any kind of arbitrary value. In that case, what should be the alpha for the phase shift? Alpha should be equal to minus beta d cos of theta 0. So if I give this alpha value on the antenna array, then I would be able to get a maximum radiation pattern along the theta naught direction. So let us take one simple example, and you can easily draw the radiation pattern using the MATLAB. Let us consider uniform linear array and isotropic radiating antennas, and the distance between the antennas are d is equal to lambda by 2. Let's say I want to have broadside array. Maximum field should be at theta is equal to 90 degree, and fair array, then maximum field should be at theta is equal to 0 degree. And let's say I want to have maximum field at theta is equal to 60 degree, or null at theta is equal to 60 degree. Those kind of design I can do it from the investigation we have done in the previous slide. We can easily design such kind of antenna array, uniform linear array. So broadside array, I want to design it. I use the condition for the broadside array. What was the condition? Alpha should be equal to 0. When I do that and I plot the radiation pattern, what I am seeing is that I have maximum radiation along theta is equal to 90 degree. Maximum radiation along theta is equal to 90 degree or minus 90 degree. So from here also, this is the polar plot, this is a rectangular plot. So what you can see is at pi by 2 or minus pi by 2, you have a maximum radiation. At other places, you have a side lobes. So there was a condition alpha should be equal to 0. Let's say if I want to have n-fair array, then what should be the condition? The condition is that alpha is equal to minus beta d. If I give alpha is equal to minus beta d, I will have a maximum radiation along theta is equal to 0. You can see that we have maximum radiation at theta is equal to 0 and theta is equal to pi. So this kind of radiation pattern are called n-fair radiation pattern. Even for the polar plot also, you can see that at 0 is equal to, and 0 and pi, you have a maximum radiation pattern. Or let's say if I want to have the antenna radiation pattern to direct along any arbitrary direction, say let's say 60 degree. We want to have maximum radiation along 60 degree. What condition I should be giving? I should be giving alpha is equal to minus beta d cos theta 0. Theta 0 is 60 degree now. So you put that, then you get the alpha, then you can do simulation in the MATLAB. What we are observing is that the radiation pattern is having maximum radiation along theta is equal to 60 degree. We are seeing that even in the polar plot and the rectangular plot, I am having the maximum radiation pattern here. This is minus 60 degree, this is also minus 60 degree here. So according to our wish, after the antenna is manufactured, we can have proper amplitude and phase of the current you give to the antenna array, especially the phase. If you change the phase of the current you are giving to its antenna element, you can change the radiation pattern of the antenna according to your wish. That's a liberty we are having for antenna array. But for a single standalone antenna, once you manufacture it, radiation pattern is fixed, you cannot do anything. But in the antenna array, depending on what phase you are giving to each element, you can have a different radiation pattern. So people usually call this also as phase antenna array. So you can even have a null at 60 degree. So in that case, the condition for the alpha should be designed according to this formula here, 2n pi by capital N minus beta d cos of theta null. Theta null is 60 degree. You plug it in, you take alpha from this value, you can take any value of n, 1 2 3 4 5 and so on. In that case, what you are observing is that we don't have any radiation along the 60 degree direction or minus 60 degree direction. So along the 60 degree direction you have a null. So according to our ways, we can tune the direction of the antenna array. So this was actually one of the motivation for the smart antenna array. Let's say you want to send signal in one particular direction, and you don't want to send any signal in one particular direction. Let's say you want to send signal in theta 1 and you don't want to send signal in theta 2. So you have to design your antenna array, give the phase, you have to design the phase of the antenna array so that it should have maximum radiation along the theta 1 and no radiation along the theta 2. So in that case, if I want to send a signal, our desired user is along the theta 1, desired user will be getting all the signals. Let's say I have another user with whom I don't want to share any information, I will not be able along the theta 2 direction. So theta 1 is where you have the intended user, theta 2 is the angle at which you have a unintended user. You don't want to share any information to the user 2 which is at theta 2, and you have a user 1 which is the intended user in which you want to send the information. So you have to design your antenna array such that it should direct the maximum radiation along the theta 1 direction and null along the theta 2 direction. So this was the concept for the smart antennas, and the smart antennas actually are the precursor for MIMO antenna arrays or MIMO wireless communication. So when I was doing my PhD at the NTU, a smart antenna was one of the latest area of research. So it's basically you are making the antenna intelligent. So antenna would be able to fine tune its direction to the intended user, the maximum radiation and no radiation to the unintended user. So some kind of smartness into the antenna. So people usually call smart antennas. You can even have planar antenna arrays. Instead of arranging antenna in one line, you can arrange the antenna array in a plane. So this diagram shows that. So now you have along the y-axis you have m elements, along the x-axis you have n elements. So total number of elements here will be m by n. So this is a m by n planar antenna array which are positioned along the xy plane. So now you can also find out the array factor for this kind of planar antenna array. These are Hertz dipole. You are assuming this red dots here are Hertz dipole. Distance between the antenna here in the x direction is dx, in the y direction is dy. So you can find out the array factor. So basically what you can do is you find out the array factor for the x element array, and you also find out the array factor for the y element array. You multiply those two, you get the array factor for the planar antenna array we have considered. So one of the major advantages of this planar antenna arrays is you can do beam scanning in both theta and phi. So in the previous example, when you have a uniform linear array, I can do beam scanning for different values of theta. But here, when I have this kind of antenna array, planar antenna array, I can do beam scanning over both theta and phi. So this is one major advantage. So if you want to find the array factor for this planar antenna array, you find the array factor for one of the element array. So for example, this element array, you find out the array factor, this element array, you find out the array factor, you multiply those two, you get the array factor for the overall m by n planar antenna element. So you know that array factor for the uniform linear array is 1 by n sine of n by 2 psi x divided by sine of half psi x. For the antenna array along the x-axis, for antenna array along the y-axis, that would be 1 by capital M sine of m by 2 psi y divided by sine of psi y by 2, where psi x is beta dx. Dx is the distance of the antenna elements in the x-axis. So beta dx sine theta cos phi plus alpha x. Alpha x is the phase shift you are giving for the antenna element along the x-axis. Psi y will be beta dy sin theta cos phi plus alpha y. Dy is the inter-element spacing along the y-axis, and alpha y is the phase shift you are giving for the antenna element array along the y-axis. So you can find out the array factor like this. You can even have a circular arrangement of antenna array. So this is what you have here. You have a circular element arrangement of an antenna array. How many of them are there? N of them is there. You position the first one here, then at the equidistance, distance should be fixed. So this distance, all of them are same. So along this circle you have positioned it. The radius of the circle is a, and you are interested in finding out the radiation pattern at the point P. Is that okay? So if you want to find the radiation pattern in the point P, what you do is these are Hertz dipole, these red dots are Hertz dipole. You find out the radiation pattern of a Hertz dipole and you multiply by the array factor. So array factor, you multiply with the radiation pattern of an antenna element, you get the total radiation pattern of that antenna array. So let us find out the array factor for this circular antenna array. So the array factor for this circular array is simply turns out to be in exponential j beta a sin theta cos phi minus phi n minus sin theta 0 cos of phi 0 minus phi n. What is phi 0 and theta 0? Phi 0 and theta 0 are the angles of the main beam. So this is the angle of the main beam where you want to have the main beam direction, that we will call it theta 0 and phi 0. What are phi n and theta n? What are phi n? Phi n is the phase for nth element. In is the excitation coefficient for the element. In is the excitation. For antenna 1 it will be I1, antenna 2 will be I2, and phase shift will be phi 1, phi 2, phi n, and so on. A is the radius of the circular array. So from here you can find out the array factor for the circular array. If you are interested in the derivation of this, you can follow the Balanis book. And let's say you can even have non-uniform arrays. Till now, whatever the arrays we have considered, the inter-element spacing between the antenna elements are always fixed. So this kind of array we have considered is called uniform array. We can also have non-uniform array. Simplest example is the binomial array. For example, for the binomial array factor will be binomial expansion of this 1 plus exponential j psi to the power n minus 1. You know binomial expansion of this, you'll have 1 plus n minus 1 exponential j psi plus, and so on. You will have an infinite term here. It's a binomial series, so you will not have infinite terms here. And this is the first term, second term, third term, and so on. You'll have nth term here. So it's a binomial series. So side lobes equal to 0 for d is equal to lambda by 2. One of the good thing about the binomial array is that you can suppress the side lobe to negligible extent. If your distance between the antenna array element is lambda by 2, d is equal to lambda by 2, side lobe will be equal to 0. There is no side lobe. As you know that signals which has gone to the side lobe is useless. No? We are wasting our power, energy. So you can suppress side lobe to 0 when d is equal to lambda by 2. But one of the major disadvantages is that such kind of antenna array will have larger beam width and lower efficiencies. So nowadays there are many antenna arrays which are depending on the application. You will have MIMO antenna array, full duplex antenna array, ambient back scattering antenna array, energy harvesting antenna array, reconfigurable antenna array, or I mean you can think of many uses of antenna array. So the point is that when you consider antenna array for one particular application, pattern multiplication principle is not everything. So you have other parameters which come into picture for different applications. So for different applications, antenna array parameter, see, you know that antenna has some parameter to specify about its performance. Just like that, antenna array also has some specific parameters to describe about its performance, and you can find out the radiation pattern of antenna array by using the pattern multiplication principle. That's all we have learned till now, but nowadays we have many antenna arrays for different applications like MIMO applications. I have listed down some of them. You can keep on doing that. So now I will actually particularly show you that this antenna array parameters will be different for different applications by taking one specific example of MIMO antennas. So you must have come across this MIMO system nowadays. This is one of the latest area of research in the MIMO wireless communication. If you want to explore, you can explore this. I have another book written on MIMO wireless communications, fundamentals of MIMO wireless communication, published by Cambridge in 2017. So basically, what is the two advantages of MIMO system? See, basically in the single antenna system, you have a transmitter. You will just have a single antenna. You will also have a receiver with a single antenna. So now in the MIMO system, the major difference is that you have multiple antennas at the transmitter and multiple antennas as the receiver. So in this particular examples, this is called 3x3 MIMO system. I have 3 antennas at the transmitter and 3 antennas at the receiver. I can have any number of antennas at transmitter and receiver. So what is the advantage of increasing the number of antennas at the transmitter and receiver? That is what is given by the that's what I'm going to explain you now. There are two types of gain in the MIMO system. One is called diversity gain, another is called the rate gain. What is the diversity gain? Diversity gain is basically when you have multiple antennas at the transmitter and multiple antennas at the receiver, the signal which you are sending from the transmitter so can go with different paths. For example, you send a signal from antenna 1, it can go to antenna 1, 2, 3 at the receiver. So signal you have sent from antenna 1 can go to antenna 1, 2, 3. Signal you have sent from antenna 2 can go through antenna 1, 2 and 3 at the receiver. Similarly, signal you send from the antenna 3 can go to antenna 1, 2, 3 at the receiver. So how many number of possible paths you have for the signal now? You count the numbers, 3 into 3, 9. So now if you have a single antenna at the transmitter, single antenna at the receiver, the number of paths signal can go, the channel you have is only 1. But here when you have multiple antennas at transmitter and receiver, channel you can have, the signal path you can have is 9, 3x3, 9. So what is this advantage of this? Let us see that that will be shown in the next slide. So now what is the advantage of this diversity gain? So the number of independent paths signal take is called diversity gain. So now let's say you send the same symbol from antenna 1, antenna 2 and antenna 3, or you send the same bits. So antenna 1, 2 and 3 are sending the same bits from the transmitter. Let's say 0 is sent from antenna 1, 2 and 3. So now this 0 bit would be able to follow many paths. 9 paths are there. Let's say one of the path is blocked. Cross sign means one of path is blocked, so signal won't be able to reach this antenna here. Again, this is blocked, so signal won't be able to reach this antenna here. But now you have the remaining 7 paths where signal can reach the antenna at the receiver. So whatever bits you have sent from the antenna transmitter would be able you can decode this at the receiver without any difficulty, because even if this part are blocked, signal has gone through the remaining parts, 7 paths. So in that case, this receiver would be able to say that 0 bits had been sent from transmitter. Had it been one antenna and one antenna, let's say antenna 1 and antenna 1, we have only one path here, and if this path is blocked, then signal you have sent or bits or symbols you have sent from the antenna 1 won't be able to reach this antenna 1. In that case, receiver won't be able to decode the message which has been sent from the antenna 1. So that is the major issue. Let's say if you have a single antenna at the transmitter and single antenna at the receiver, whenever there is problem with this part you have here, you won't be able to detect the signal. You won't be able to decode the message which has been sent from the transmitter. But now when you have multiple diverse part here, signal which has gone from this antenna, this antenna, this antenna would be able to reach the receiver, and you can decode the message properly. So this is called diversity gain. Number of independent paths you have here is called the diversity gain. So one of the gain of the MIMO system is diversity gain. You will have many diverse paths of the signal to reach from the transmitter to receiver because of the multiple antennas at the transmitter and receiver. So there is another gain here which is called multiplexing gain. So in the single antenna case, what do? Let's say you have a transmitter, there will be one single antenna here, one single antenna here. So you will be able to send signal from this antenna only, because you have one antenna here, one antenna only. You will be able to send bit 1 here, then 1 will be received by this receiving antenna. So in that case, you will be able to send 1 bit at a time. This is a simplified example so that everyone can understand what is multiplexing gain. So now let's say this transmitter want to send 0, 0, 1, and transmitter has 3 antennas, antenna 1, 2 and 3. What this transmitter will do is, this is a series bits you convert into parallel. So this first antenna will send 1, second antenna will send 0, third antenna will send 0. So at one particular instant of time, this 3x3 MIMO system is able to send 3 bits at a time. Had it been only one antenna at the transmitter and one antenna at the receiver, only 1 bit could be sent at one particular instant of time. But let's say you have 3 antennas here, then you will be able to send 3 bits at a time. So the gain in terms of this is called multiplexing gain or rate gain. So the speed with which you can send the bits from the transmitter to the receiver increase linearly with the number of antennas. If you have 3 antennas, speed will be thrice. If you have 4 antennas, speed will be 4 times with that of the conventional wireless communication system which employ one antenna at the transmitter and receiver. So now MIMO has 2 gain. One is diversity gain and another is the multiplexing gain or rate gain. So that's why people are doing a lot of research about the MIMO system. It can increase the speed of the transmission of message bits from the transmitter to the receiver, and it can also overcome the limitations of the single input output system where you have only one part. You can have diversity gain. Using diversity gain, you will be able to send out the same bits along different paths so the receiver can easily detect the message. So in all of this, what you can observe is that this signal you are transmitting from the antenna 1 should be going to antenna 1 only. Antenna 2 should be going to antenna 2 only. Antenna 3 should be going to antenna 3 only. So now here we actually want the channel of this antenna 1, antenna 2 and antenna 3 to be completely independent. Even if we have multiple antenna at the transmitter, I want signal which is going from antenna 1, antenna 2, antenna 3 to be completely independent. Then only whatever explanation I have done is successful. So we want to have minimum interaction of antenna 1, 2 and 3 at transmitter as well as the receiver. They should be, in ideal case, they should be independent. Then only we'll have that rate gain. Similarly here also, I want all these parts should be independent. One part and another part, signal which is gone from this part, signal which is gone from this part, they should not be correlated. So I want maximum independence of all the parts here. So the idea of designing MIMO antenna array is going to be different. So what we did was, in the antenna array principle, what we have is we have one port, and from the one port we are feeding to the antenna array. The feed line is giving different phases to all the antenna elements. But here, instead of having one port, we'll have 3 ports. From every port we'll be sending signal. For example, in this case, I have 3 antenna. I will have 3 ports. I will send one signal, one message from one port, another message from another port, another message from another port. So this will be a 3-port antenna array. So antenna array here is no longer a single port antenna array. It is a multi-port antenna array, and all the antenna I want to behave differently. That means independently. There should be minimum correlation between the antenna 1, 2 and 3. So the parameters for designing the modern antenna array turns out to be different. For example, if you consider MIMO antenna array, what we want is something called, we have different parameters for designing MIMO antenna arrays. One parameter we consider for designing MIMO antenna array is called the envelope correlation coefficient. So envelope correlation coefficient actually gives you an idea of correlation between the antenna elements. For example, you have 3x3 MIMO system. What is the correlation of antenna 1 to 2, antenna 1 to 3, and so on? That correlation coefficient is given by this. So envelope correlation coefficient is defined like this. This is the 3D radiation pattern of the ith antenna. This is the 3D radiation pattern of the jth antenna. And yeah, the omega is the solid angle. So you can find out correlation coefficient like this from the 3D radiation pattern of the ith antenna and z antenna. This is the envelope correlation coefficient of the ith and z antenna. So now lower is the correlation coefficient, it's better for us. So now another parameter is there. So basically in today's world, all the antenna arrays you want to make it smaller and smaller. So all the device you carry, any portable device, you want to make it smaller and smaller, and most of the device nowadays are trying to exploit the advantage of antenna array. So you want to fit in any device antenna array, you should not have a big size. Basically small size is very attractive feature nowadays. All the device you make, you want to make it smaller and smaller. So in that case, you still want to exploit the advantage of MIMO antenna array or any kind of antenna array. In that case, you need to fit in the antenna array in a small volume. So the spacing between the antenna elements need to be reduced. So let's say you have your mobile phone. Your mobile phone is working around 1 GHz. You find out what is the wavelength. You find out the wavelength at 1 GHz, and let's say you want to make the conventional antenna array, distance between them will be lambda by 2. So you'll realize that from the conventional array you won't be able to fit in 2 antenna elements on your mobile phone. You can do calculations of that and you can see. And the size of the mobile phone is too small to fit in a conventional antenna array of lambda by 2 spacing between the antenna elements. So now in that case, we are doing a lot of research with one of my PhD students. We are trying to explore the antenna array in which the spacing between the antenna array is smaller and smaller. We have gone up to 0.1 lambda distance between the antenna array. Usually conventional is lambda by 2, but we have reduced the inter-element spacing to around 0.1 lambda. Then in that case, there is one major problem here. When you reduce the size of the antenna array, you keep the antennas closer and closer, all the antennas start interacting with one another. So let's say you have 2 antenna element array. How do you see whether how much is the coupling between one antenna to another antenna? What you do is you basically excite one of the antenna and see is there any signal picked up by the second antenna. So you know that, let's say I consider 2x2 MIMO array. So I will have 2 antennas at the transmitter, 2 antennas at the receiver. I want to find out the mutual coupling between the antenna elements for the transmitter. So transmitter has 2 antennas. So it's a 2 element array. So all the transmitting antennas, 2 are there. I will have 2 ports. I connect port 1 to the antenna 1 and port 2 the antenna 2 of the 2x2 MIMO antenna array. So now what I do is I actually put the signal in port 1 of the antenna 1, and antenna 1 will be radiating signals in the free space. And what I do is I do not give any excitation on the port 2 of the antenna 2, and simply I put a match slot to the port 2 of the antenna 2, and I want to find out how much signal is coming to the antenna 2. So that way I can find out mutual coupling between the antenna arrays. This same principle you can extend it for n by n MIMO antenna array or any kind of antenna array. So if you want to find mutual coupling between the ith and z antenna elements in an antenna array, what you do is you drive the port j with an incident wave of aj and measure the reflected wave bi, which is coming out of the port I. So Sij is bi by aj when ak is 0, k naught is equal to j. So when you are just exciting this port, you are making all other ports without any excitation, and you just put match slot there and you find out Sij, you would be able to get the mutual coupling. That's how you measure it. Let's say mutual coupling for the 2x2 MIMO antenna array will be let's say I want to find mutual coupling 1, antenna 1 and antenna 2, that will be S12. So in that case I can just excite either antenna 1 or antenna 2 and put the other one match slot and measure the scattering parameter. So what we will observe now is that antenna array for modern application will have different parameter for the different applications. So antenna array parameters is going to be different for different applications, and one of the major widely used parameter is mutual coupling for a closely packed antenna array. When you place the antenna elements together very closely, antenna start interacting. So what you do is you design some techniques to reduce this mutual coupling. So that is one of the major research area in the antenna arrays nowadays. That's all for this class. Thank you very much.